Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to find the area of a polar region. In fact, finding the area of a region in XY coordinate system was one of the prominent applications of the integral concept, the definite integral concept. So right now we're given polar equations. We're in polar coordinate system, and first, sketching the region is one of the most important parts of attacking this type of problems. And let me just tell you a few things before we start. So we're going to use the unit circle all the time, so it's better to have this with you somewhere in your notes. Please keep it because I will refer back to this within the video. And also, remember how you go from polar coordinates to rectangular or rectangular to polar coordinates. So this table tells you how you transform one into another, and as well when you're talking about area and polar coordinates, as I said, we had to redefine the area concept that we had earlier. So here we go. We wrote the area concept for a polar equation, r equals f of theta. And as you see that we're talking about the area stuck in between the rays theta equals alpha and theta equals beta. So essentially, this is what we're gonna sort of like work through for the rest of the video. And I want to give you a few like heads up before we start. So here is r equals 3 cosine theta, and we're asked to find the area of the interior of 3 cosine theta. Well, 3 cosine theta is a circle. You can go ahead and find the area of a circle by using the known formula from geometry, pi r squared. But we're going to do this by the help of integration. And let's see what the other graph looks like. We're going to find the area of two panels of this graph, polar graph. So I shaded three of them, but we're going to find the area, some of the areas of two of them. Okay, so and I don't want to give you more heads up because I want you to watch the rest of the video and see what I'm going to do for each part. So, well, let's get started because we have a long way to go. All right, let's start. We're going to find the area of the region, which is the interior of r equals 3 cosine theta. Just to give you some heads up, the area formula in polar coordinates is different. So let's say like we have the radial lines theta equals alpha and theta equals beta, and we have the polar equation. Let's say r equals f of theta. So the region bounded by the graph of r equals f of theta, and the radial lines theta equals alpha and theta equals beta. So it's surrounded by three different curves. Let's put those as like curves, okay? So that area is found by this formula. It's essentially 1/2 the integral from alpha to beta r squared d theta, okay? So this is slightly different from what we had in chapter 7 when we were trying to find the areas between the curves, okay? Well, area or areas between the curves. All right, and not just for this question, but for other questions as well, like part B and part C, I'm going to use the unit circle whenever it's applicable. So because these are the unit circle provides you the x and y values, like cosine and sine values, essentially, for certain known angles. And the way you read it is like, let's say like you have a point here that corresponds to theta equals pi over 3. So the x coordinate at that point is cosine of that angle, and then y coordinate is the sine of that angle. So I'll refer back to that. And let's go back to the graph of r equals 3 cosine theta. And if you have your TI-84 with you, please first set it to the polar form and graph this function and see what it looks like. Once we had the graph, we had to look at it in an educated way to determine what the alpha and beta in the area formula are. So here is what I got here. Okay, here's what I got. All right. So here So let me just write here, theta equals 0. And I also put those lines here, okay? Those rays, in fact, right? And we call them like radial lines, okay? So these are the radial lines. Theta equals 0, theta equals pi over 8, and on and on and on. So what you do when you try to graph the circle by hand is that you go ahead and you look at the R values for different radial lines, okay? So for example, you have theta here, you have R here. If you have a little table here, you list, let's say, theta equals 0, pi over 4, pi over 2, and on and on and on. And you just want to see the orientation in this graph and then see what the what like one period is in total, okay? So here we go. So let's say like theta equals 0. So that means I'm on this radial line here. So I want to know what R is. So that's 3 times cosine 0. That's exactly equal to 3. So that means I'm right here. Okay, I start from here. Okay, for theta equals, let's say, pi over 2. Okay, you have 3 times cosine pi over 2. We're right here. We're right on this ray here. This is also another known angle. And 3 times cosine pi over 2 takes you to 0. Okay, so it takes you to 0, which essentially means that this is 0. So on the graph, what it means is you just go in this direction and you go to theta equals pi over 2 ray, and then you just don't walk any units on that. So it's R equals 0, so you're just right at the origin. So you follow this trajectory all the way to 0, from 0 to pi over 2. So the half of the circle is in fact for theta starting from 0 to pi over 2. And you can go all the way to pi to see what's going on. But for cosine pi, we have R to be -3, right? Because 3 times cosine pi, we have -3. And theta equals pi is right here. So that ray is right here. So that means R equals -3. I'm going to walk 3 units to the right, exactly the opposite side, okay? So walking 3 units to the right takes you back to where you start. So that means starting from this black point here, so I'm going all the way in this direction. So one loop of this circle is done for thetas in between 0 and pi, okay? So so what that means is when I have my ray all the way rotated like this from 0 to pi, right, I can in fact graph the circle all the way. So for that reason, in the formula of the area, I'm going to take alpha to be 0 and beta to be pi. I have 1/2. I have r squared d theta. So let's, all right, so then 1/2 0 pi. This is 9 cosine squared theta d theta. So now we're back to integration business again. So we have to remember how we integrate the even powers of sine or cosine. And we had this power reducing formula for cosine. So I'm going to use that one. So that's 1/2 integral from 0 to pi. You have also 9. You can pull that out. Cosine 2 theta plus 1 over 2 d theta. Okay, so this is just the power reducing formula for cosine. And here we go. So 9 over 4. I've also pulled this out. Okay, 9 over 4. Now I'm integrating it. 1/2 sine 2 theta, right? Sine 2 theta plus theta. Okay. So this is from 0 to pi. Okay, that looks good. All right, so I'm gonna plug in. 9 over 4. I'm gonna plug in pi first. So 1/2 sine 2 pi plus pi minus 9 over 4. 1/2 sine 0 plus 0, essentially. Okay. And the only term that survives here is this one, because all other terms are 0. Okay, because sine 2 pi, sine 0, they're all 0. So we got just 9 pi over 4. Okay, so going back to this graph here, we can immediately conclude that this area is nothing but 9 pi over 4. Okay, so the area here is 9 pi over 4. All right. You could also be asked the area of a certain portion of this circle. Then you have to determine the alpha and beta, the rays, so that your area is sort of like stuck in between those rays and obviously between the curve as well. Okay. I think that takes care of part A. So let's move to part B in another video, and I'll see you there. Bye.